that are funding the instrument development from research labs in France, and the balloon platform and operations, and also the much of the science that's that the French groups are working on. But it is a close collaboration between scientists on both sides. Let's see, next. So this is these three lines that are shown on the globe here are paths from early tropical test flights of the superpressure balloons in 2010. It was in preparation for an Antarctic campaign. The flight duration was approximately 80 days, and the balloons were flying about 20 kilometers altitude. And you can see that some wave structures are visible directly in the balloon paths. And you can also see that here the QVO changed phase during the time period when the balloons were flying. And so we can see that, as well as different scales of waves that are affecting the balloon trajectory. So the platform is an excellent one for observing these type of waves, and the focus of this campaign is the tropical tropopause layer, which shown over here in a reference from Fuglestaller, between 14 and 18.5 kilometers. It's the gateway from the troposphere into the middle atmosphere, and it sets the chemical composition of the stratosphere, in particular for water vapor and ozone. As air parcels rise, for example, through convection, through this layer, because it's the coldest layer, the air parcels dehydrate it, and so that controls how much water vapor gets into the stratosphere. And there are large decadal variations, and the presence of these cirrus clouds that form in this layer influence and modulate surface warming. From a dynamical point of view, the TTL is very rich in a range of scales of waves and other processes. These are what the focus of the research is on, trying to get more information about deep convection and cirrus cloud formation, planetary scale, and Kelvin-Rossby and Rossby gravity waves. And also these waves influence the quasi-biennial oscillation that I showed on the previous slide, which is the direction that the winds are blowing in the stratosphere. So a significant part of our knowledge of what's going on in the TTL relies on NWP model analyses, and because of the sparsity of wind observations, especially at upper levels over the oceans, there are pretty high errors. This is just the errors in the initial conditions in the ECMWF model at 300 hectopascals, and there are areas where the errors are quite large in the tropics. So in some of the previous field campaigns with balloons, the gravity wave measurements were the objective of the campaign. And I'm just going to go through a couple types of measurements that have been made and were made on balloons, and what particular process they're relevant to. And then Martina is going to talk a little bit later a bit more about the modeling component of some of these. So gravity wave momentum flux in the tropics, there's activity going on at a large range of scales, and so measurements are needed that measure all these scales. This information goes into the parameterization of the momentum flux and the gravity wave drag in climate models, for example. So we need to know these properties, and in the past campaigns, these observations of in situ pressure, temperature, and horizontal velocity of the balloon, which is traveling as a Lagrangian tracer of the air mass. So the horizontal velocity of the air mass. These variations are used to derive measurements of momentum flux, and those are used in climate models. So these previous publications by some of the members of our team relied on just vertical measurements and in situ measurements that don't give a very clear picture of the three-dimensional variability of waves. What we'd like to do with this campaign is expand it to understand more about the relationship between waves and convection. This is a reference from Kaladis that shows the wave speeds and wave number and period of different types of waves in the tropics. And so this is from brightness temperature of geostationary satellites as a proxy for convection and convectively coupled waves. And so to go beyond, what we want to do to go beyond this is to make measurements of horizontal wave properties, not just the vertical. This graph on the left shows that if you try to model the occurrence of gravity waves and then make measurements of them in 2D, you would get a very different value than you would in 3D. So the idea is that and we only have measurements in 2D as we're flying along if we're just making the in situ measurements, just along the flight track and in the vertical. So what we're trying to do by adding, in particular, the instrument, the radio occultation instrument, is that it's going to give profiles in the region of the balloon. For example, if they have a balloon trajectory here and a wave field with a wavelength maybe of about 600 kilometers, as the balloon is floating along this trajectory, it's making a measurement of a profile at one of these points, depending on where the signal source is in the sky, the GPS satellite that's the signal source. And so as it floats along, we get a lot of measurements in space that can help us to determine the 3D variability of temperature and try to derive wave properties. The floats instrument is another instrument that we're trying to use to get more detailed information on the waves, in particular in terms of what's going on at the cold point tropopause. So the floats instrument is a fiber optic cable that hangs 2 kilometers beneath the balloon and measures temperature every 5 meters down the cable. And so as the balloon's flying around, you get with time, you get a profile of temperature structure. This particular image was from a test they did from a tower, but just to give you an idea that it's going to provide a curtain of temperature profiles as it's flying along. And hopefully we'll be able to see different periods of waves in fine detail at the cold point tropopause. And then we are going to have several instruments that will provide some information, additional information on what's going on at the tropopause in terms of dehydration and cirrus formation, in particular the ratchets instrument that is just a line that reels down 6 times per night and makes measurements of temperature, water vapor, and also cloud particles. The observations, the in situ observations of the balloon location are also used to make, well, they are a measurement of the wind at the altitude of the balloon, and those are have been in the are going to be assimilated into the ECMWF and Meteo France weather prediction models in real time. So that will, and they will be available for the reanalysis data assimilation. So this helps address the earlier question about those large errors in the wind fields in the stratosphere, over the oceans in particular, and this will be useful for the validating the EOS satellite. It's 3D wind lidar. The one example of the wave impacts on horizontal velocity of winds in the equatorial region is shown here. This is once again that preliminary campaign data in 2010, where when these waves were present in the stratosphere, the balloon winds varied quite a bit from the reanalysis winds that did not have the balloon data in it. So there is definitely information that we want to improve in these models. So the weather prediction and the data assimilation and the CalVal is something that's beneficial, but it's not really the focus of the science of the campaign. But we do want to take advantage of the opportunity to disseminate that information that way. These will be flying 2 campaigns, 20 balloons in each campaign, and then an additional campaign this fall to test the instruments. So 10 balloons will be flying at 20 kilometers. That'll be doing mostly remote sensing and dynamics. It's got a LiDAR that can detect cloud tops, the radio occultation instrument, a radiation instrument, and the in situ temperature instruments. And then the lower balloons, there'll be 10 of those at 18 kilometers, and they're the ones with the new water vapor sensors and the reel down sensors and the floats 2 kilometer long fiber optic cables. So these are flying low enough that these 2 kilometer cables will get a good sample of the TTL. I put this in here for your reference, all of the details on the different instruments that will be flying. And then I put in a slide here that shows what we're doing with the campaign this year in November. From November to February, we're flying 6 balloons. That's 1 of each type, because we have 3 different instruments on each balloon, just to make sure that they're all functioning. But we do really hope to get science data out of this, and Martina in particular is eagerly awaiting some of these observations. We did make an effort to make the community aware of this upcoming campaign. This is the cover of the EOS Buzz, newsletter, and we just like to talk about this French-US collaboration and how it goes back in history to these days when we were dreaming about doing these things in balloons, even though there was no balloon in the book Around the World in 80 Days. So that's just for fun. And then this is some of the past workshops and meetings that we've had to make the people outside the direct collaboration aware of what's going on with the Strateole-2 program. And we're planning to have an early science preview workshop at Scripps in September 2020, where we'll get a look at this campaign validation data and hopefully some of the science that came out of that. So just summary of these science objectives that we're trying to get at with the balloon campaign, and then and I just want to make the point that this campaign, there are a lot of new instruments that have been developed especially for this campaign, so it's a little different from some of the other integration of observations and modeling. We're having also to deal with, just the instrument development. So modelers are champing at the bit here, and I'll turn it over to Martina, who will talk about some of these problems that they're trying to get at with the modeling. So now I quit pointing on the screen, and Martina can now. Is that how it works?
Yes. Thank you, Jennifer, for the introduction and the overview. So I'm going to present you now some processes that could be addressed based on the campaign data of the Strateole-2 campaign observations. And one of these processes is the representation of planetary scale waves, such as the Rossby waves or the equatorial Kelvin waves. Their horizontal structure is very well resolved in climate models. However, the vertical structure of these waves is not resolved due to a resolution of about 5 kilometers in the vertical in the climate models, and this can lead to large errors in the representation of these waves. With the highly resolved 3D observations of the Strateole-2 campaign, we would have a new data set available for comparison studies to improve their representation in the climate models. Jennifer has already talked to my second point, so I'm not going to go into any more details with that. I just want to mention quickly that the Strateole-2 observations will help to improve the weather prediction during that time frame, as the data will be operationally assimilated to the ECMWF and the French forecasting model. Another process which would benefit from these observations will be the QBO representation in the climate models. Again, a key component here is the vertical representation of the Kelvin waves and the Rossby waves, which are essential drivers of the QBO in the equator region. And due to the high resolution of the vertical observations of the Strateole-2, we have the opportunity to study the interaction of these waves with the mean flow, and therefore also this data set is a new opportunity for the QBO initiative for comparison studies in order to improve the parameterizations of the equatorial waves to further improve the representation of the QBO in climate models. As Jennifer has also mentioned, the data at hand could improve the cirrus evolution in the models, because Strateole-2 will provide a highly resolved temperature measurements in the tropopause region, and this could help to tune parameterizations of this temperature variability in climate models. Last but not least, I want to mention also the link between gravity waves and convection. In the equator region, especially, the convection is one of the major generation processes for gravity waves. And these gravity waves need to be parameterized in climate models, but also in numerical weather prediction models. especially their flux and the gravity wave drag based on these convective gravity waves. And at the moment, as far as I understood it, there are two different approaches for the parameterizations out there in the model world. One older approach uses a homogeneous distribution of the launch drag for the convective gravity waves, no matter whether there is a source actually present or not. And the newer approach uses kind of a more source-dependent distribution to launch the convective gravity waves in the models. And with the observations that Jennifer has already mentioned regarding the cloud tops, for example, we could help to improve these parameterizations that take into account more a source-dependent distribution of the launch flux. The challenge here is that numerous studies have already realized that the vertical shape and the vertical structure and spectral characteristics of the convective gravity waves are tied to the shape and the profile of the latent heating. However, the latent heating cannot be directly observed, and therefore we have to infer the latent heating profile from by other means. And what we plan to do, also based on the Strateole-2 data set, is a study which I have recently started based on an approach by Stefan and Alexander in 2015, in which they trained an algorithm to characterize the vertical profile of the latent heating based on rain rates. And what they did in their study was to use a full physics cloud resolving model to simulate the gravity wave field and the latent heating profiles together with the rain rates, and they associated the latent heating profiles with the rain rates to create an algorithm where they could determine based on a certain rain rate which latent heating profile is valid. So what they actually did is then they could realistically reproduce characteristics of a gravity wave field based on these lookup tables or this algorithm, and they could apply this algorithm to realistically reproduce gravity waves which were observed during a mid-latitude summertime storm over the continental US. And what we plan to do is to extend this approach to the tropics. And what we also plan to do is to extend this to associate the latent heating profile not only to the rain rates, but also to the ecotop heights, which can be measured by a radar. And that's the strength of these approaches, that we would, so to say, only need the observation of the rain rates and the ecotops. And from these measurements, we can then infer based on the full physics cloud resolving modeling outputs the latent heating profile. And with these latent heating profiles, we could then excite realistic convectively generated gravity waves in the tropics. And in our study, what we use is an ensemble of four full physics runs. We also use the WRF in an idealized mode in order to study the impact of including the ecotop height to the lookup tables. And then we use sea-pole radar measurements in Australia to initialize the idealized WRF simulations, and EOS measurements are used to validate the gravity wave field which is generated by the idealized WRF simulations. And the map on the right-hand side shows the model domain 3 model domains. We use 2 nests, and the latent heating profiles are associated to the ecotop heights and the rain rates in the innermost domain, which has a resolution of about 2 kilometers. And fresh from my printing program, I want to show you a couple of slides. The first are histograms based on the full physics WRF simulations. On the left-hand side, the y-axis shows the ecotop and the x-axis the precipitation rate. And the color coding refers here to the number of occurrence or number of points per bin. And what I just want you to acknowledge here is that high precipitation rates seem to be on the one hand as sparse events, rather low number of occurrences are associated with high precipitation rates, and on the other hand, these high precipitation rates seem to be associated with deep convection. And when we take into account the histogram on the right-hand side, in here the color coding refers to the latent heating. We also see that the largest values of the latent heating rates are associated with these high precipitation rates and high ecotop altitudes. In a further step, I created the lookup table based on these 4 WRF simulations. And on the left-hand side, I show the lookup table associated to ecotops ranging from 13 to 19 kilometers, so to rather deep convection. And in these plots, the y-axis refers to the altitude. In the middle, I show the lookup table for the ecotop ranging from 7 to 13 kilometers, and for 2 to 7 kilometers, the lookup table is shown on the right-hand side. And again, we see that enhanced latent heating is related to the high precipitation rates and the deep convection, as is shown here. The majority of the latent heating seems to be concentrated between 3 and about 13 kilometers. And with decreasing ecotop heights, we can see this analysis shows that also the latent heating and the precipitation rates decrease, as these 2 lookup tables show. Based on these lookup tables, we ran initialized, idealized WRF simulations in order to simulate the gravity wave field. And on the left-hand side, I show you horizontal momentum fluxes based on this idealized simulation, which was initialized with a lookup table that only is associated to the precipitation rates. I refer to that as the 1D lookup table. And on the right-hand side, I show you a 2D lookup table simulation where the lookup table was also additionally associated to the ecotops, as I have shown you in the previous slide. And this is a very, very new analysis from basically yesterday. And what I want to highlight here is that the total horizontal momentum fluxes, the shape seems to be retained, no matter if the lookup table also contains the information of the ecotop heights. However, when we look at the magnitudes of the fluxes, the horizontal momentum flux values increase by about a factor of 10, which you cannot see here because the scaling is the same between the 2 plots, because I wanted to show you, really show you in the same scale that the momentum fluxes increase significantly when we include the ecotop heights in the generation of the lookup tables. A further step which is missing in this study, which is currently done by my colleague, is to validate the output of these idealized simulations based on the EOS measurements. And with that, I come to my summary. I want to give you 3 take-home messages. The first take-home message being that Strateole-2 campaign data will provide observations in a region where otherwise only sparse data is available. The dataset will contain high-resolution 3D observation of gravity waves and planetary scale waves around the equator, and this will provide a great opportunity to improve parameterizations from different scales, ranging from the weather prediction scale to the climate models. Yeah, and with that, I thank you for your attention.
Thank you, Martina and Jennifer. Did anyone have any questions? I know that you guys were talking about the website. Did you guys want to quickly go over it?
Oops. Where's the slide? It's on the
very end.
Okay, here. Yeah, for the campaign, we have also a website available to forecast the flight tracks of the balloons. And we put in here, as an example, a screenshot of this web page. You can see on this map here, in this case, the total precipitation based on ECMWF's forecasts, and we can calculate or we can predict on this web page the trajectories of the balloons. And I have given you here an example of 2 different trajectories based on 2 different kinds of forecasts. Therefore, they are shown in green and in white. And we will use that during the campaign in order to plan for intensive observational periods in regions where we suspect enhanced wave observational probabilities, and also if we are in regions where cirrus clouds might develop, we would use this tool in order to declare intensive observational periods. This web page also contains other information. It also contains wind forecasts and observations of different satellites, as for example the GOES satellites. And we also test, based on this campaign, a new turbulence forecasting parameter with the ECMWF, but this is only a research parameter, I should stress that. And this parameter takes into account especially convective gravity waves for the prediction of turbulence in these areas. Jennifer, is there something more that you would like to mention with this web page?
No, that's it. And then we put the link in the chat window here so that you can take a look if you're curious. And then I think that when the campaign's going on, there's going to be the actual trajectories as well as the real ones, and then you can retrieve the data from a particular balloon. Some of the data is coming in real time, like the in situ measurements. Many of the instruments are take a little bit longer to get the data back, but we hope to be able to start putting some of that on additional information onto the web page. But for sure, the in situ measurements will be there. And that's all I have to say. So you can open it up for questions now.
Anyone have any questions? Go ahead, Amy.
Yeah, I was wondering, where are the balloons launched from, and how is there a way to sort of control where they go, or how do you keep them at a certain altitude?
They are being launched from Seychelles, which is right here, Seychelles Island. We want to launch it within 5 degrees of the equator. So that the winds are primarily zonal winds, and they won't drift away too far. We don't control them. Only we can adjust their height a little bit, but we're trying to fly at a constant height, either 18 kilometers below, for the lower balloons, or 20 kilometers for the upper ones. And the balloon is actually a fixed size. It's a rigid. It's not a stretchy envelope, so the density is constant in the balloon, and that's important so that it really is acting as a tracer, and then we could use those position measurements to derive the wave properties. I have to say that we've been in contact with Google Loon. They are trying to, they're flying stratospheric balloons to try to provide internet, and it's pretty experimental on their part. But there's a little bit of tech transfer going on between our group and the Google team. And they actually try to control their balloons by moving to different altitudes. We're trying to minimize excursions in terms of altitude.
Okay, thank you. Hello? Uh-oh.
Victoria, can you hear us?
Oh, I can now. Something went down. Okay. I had just a question. We've done a number of process study webinars where people have really struggled to effectively collaborate internationally because of the different funding cycles, and I just wondered if you had any lessons learned in terms of when did you start initiating the program, and how did you get the French and US collaboration established effectively? It sounds like it's great.
I think the initial collaboration actually happened before I started working with the group in France. There was a negotiation about the TPARC campaign, and I wasn't really involved in that, but for TPARC was kind of it's a typhoon campaign, and the U.S. investigators wanted to use the balloons. And so they kind of negotiated, and in exchange, the following campaign in Antarctica that the French really wanted to do, the U.S. provided some instrumentation. So there was that history already in the background, and so that was actually some. So then I'll just talk about how we got this collaboration going, and that is basically that I met Albert Herzog at AGU, and we started talking about what we could do, and he started putting together one of these balloon campaigns and basically worked with me to develop a proposal to put on a new instrument. So we had really the science and the instrumentation contained in a proposal going to NSF. And then it really was after it was determined to be interesting that the negotiations between NSF and CNES got into more of the details, the practical details, and the budgetary details. I have to say we have a great program manager at NSF who's is very involved in the process. And then I enjoy coming to France, so the collaboration between the French and the US scientists is pretty strong, and it's very hands-on and active. So it's built on, and several of the people at Northwest Research Associates, where Martina is, they've been having science collaborations using other observational data sets on the gravity wave science with several of the people in the French labs. So it's really built on the individual relationships, and then they always seem to work out the details, the nuts and bolts between NSF and CNES after that's, the ideas are really worked out. NSF sponsored a workshop in 2013 for us to really get together and welcome other people into the project, because NSF likes to see many scientists using one big data set, not just a few scientists. So that was a key part of it as well, the workshop that we had there. No, it was 2016, not 2013, sorry.
Thank you. That's really interesting. Did anyone, if no one else has a question, I had a second question. I wondered about, it's fantastic that the modeling work is proceeding, in advance of having the instrument flying. And one of the things we've been working on is a best practices paper for process studies. And I wondered whether you had ideas on ways to facilitate that, whether it's helpful to have preliminary data as or data scraping in advance of, very early on in the proposal process, so that the modelers have something to kind of get started on before the field campaigns are going.
I think that one thing that is always really useful from my perspective, being an observationalist, is to really work with somebody to try and simulate what I'm going to be measuring in advance. It's just a huge tool for getting some insight into what's feasible and what can be done. And it's always good also to try, as Martina has shown, using AIRS data. It's not the best for getting high vertical resolution gravity waves, but using whatever's out there to try to make a first pass at it, that also helps a lot. Not only, well, they're gaining insight as well, but also it really strengthens the arguments in the proposals when you can say, we tried to look at this and this is all we have, and we've been working with that and it's just not good enough. So that's both of those parts are very useful and important. Martina, do you want to say something else about that?
No, you covered it very nicely. It's really, I don't have any experience yet in writing a proposal, so, but from my PhD, we were involved in a field campaign as well, and before that campaign actually started, they had for their proposal also what they call dry runs. So they knew exactly what they were looking for, and exactly with these dry runs they found out what measurements they would need in order to observe the patterns that they were looking for. I don't know if you've heard of the Nordics campaign. It was weather processes related. And and this is also a campaign which actually was conducted for the modeling. So in this campaign, the observational part was actually very little compared to campaigns that I've experienced before, because it was actually a campaign designed only for the modelers and the weather prediction community, and it helped them a lot too to figure out what measurements do we have available beforehand and figure out what could be improved in order to have the right data for the modelers available.
I think Mike Patterson has a question. Go ahead, Mike.
Hi, thanks, Jenny. Great presentation, and you did a very nice job of both covering the observational and modeling aspects. So thanks for all the preparation here. In your write-up, following up on the question about international collaboration, you had indicated that CNES has been working for quite some time to get flight authorization over all the equatorial countries, and so. Can you talk to us about that? You had indicated that this would be helpful to talk about here on this webinar, and what the challenges are in getting not only the flights, but also ensuring that you have access to all of the in-situ data from the tropical countries over which you're going to be flying.
Okay, so the procedure that we've used in the past, because I did do the one Antarctic campaign with the CNES in the past, the procedure that they've used in the past is requested authorization from the country through their Department of State or their equivalent, and if they don't reply, well, we ask again, but if they don't reply, the default assumption is that they don't have any objections to the flight. So in the past, most of and even in the 2010 one in the equator, at the equatorial region, most of the countries responded positively in a short time. It's easier in the Antarctic campaign. This time around, we've only so far, and they've been working on it a year probably. Well, actually, I think that even more than a year, but they just stepped up the pressure in the last year. We only have 27 out of 80 countries that actually replied. And I think realistically, it's not a very serious matter. I mean, I just can't imagine that it's got a lot of importance in all of the things these countries have to deal with, and there are some that are, currently struggling with crisis situations. So I think that so the problem is that with only 27 out of 84 currently, our last count, the French Department of State, the minister would like to see more of the countries participating, just because they think that it's somewhat risky if they don't have the majority. They can decide to authorize the CNES to let them fly the balloons, but they don't want to create any kind of incident. So they're working on every way they have to contact these different countries. They have a team at CNES now working on it. So, but they've also requested some help from NSF to make some direct contacts in the Philippines and Malaysia. So if there is an international CLIVAR representatives from these countries, and I can provide a list of countries that we haven't got response from that might be able to also comment on the scientific interest to move things along, then I think that would be useful to have that input.
So on that point about international CLIVAR, we don't necessarily in our international organization have say member countries represented in that way. We do have a climate dynamics panel though that we can raise this to their attention. as well, I think there might be through UN auspices with the WMO. I'd be surprised if the French Ministry of State isn't already working with the WMO on this, but that might be another avenue worth pursuing if that hasn't been explored.
I'm pretty sure they've got the contacts with the WMO, but that other panel that you're mentioning, the climate dynamics panel, that might be useful to see who's on there and make that information. We can make that information available to the team at CNES.
Okay. Thank you.
Thank you.
Go ahead,
I had another question if I can hop in, and it had to do with the observational, the observations that you're using for either ground truthing or comparing with the balloon-borne observations. So have you engaged with the COSMIC program at all? That's also radio occultation from satellites?
Yeah, I see those guys on a pretty regular basis at the COSMIC meetings, and so they know about this project. And Joan Alexander, Martina's colleague at NWRA, she's actually published a couple papers using the radio occultation data to look at waves. So there's lots of ways that we can use that data in addition to the high resolution. So the nice thing about the occultation on the balloon is you get a bunch of measurements in the same area.
I think you're breaking up.
Oh, I'm sorry. So the radio occultation measurements on the balloon get a lot of observations in the same air mass. So, but it would be nice, it will be good also to use the more sparse cosmic occultations. And they're just launching next week, the second constellation.
It actually just launched this morning, in the wee hours this morning. So,
oh, I thought it was July. Why did I think it was July 1st?
Yeah, no,
was it this morning?
I had it listed. Yeah, I had it listed as June 24th, but I just looked it up, and the NESDIS here just announced the launch at like 3 a.m. this morning, June 25th.
Oh,
so those are being deployed as we speak, and so there will be some. They'll have to go through their initial tests and evaluation before the data stream starts, but. There's a great opportunity. We had talked about putting it on the on our field campaign website as well, to be able to pull those up to see what's the temperature, if there's some wave activity going on that we see in the cloud structures. To just click on those. So hopefully we'll be able to do that. And as well, you'll get hopefully some higher resolution water vapor content information as well that can help you with dehydration. We don't really my observations are not precise enough to get water vapor, but even the cosmic observations at that altitude are not providing. It's really just providing temperature, and they're not retrieving useful water vapor information because it's just such a small quantity. So these other instruments that we have, that this LIDAR and the other instrument we have to measure the water vapor might be, an important set of information. Because cosmic doesn't really get the water vapor precisely enough. Okay. Well, thank you.
And I see a question from Kevin. Go ahead.
Yeah, I'll keep it quick since we're running up on our timeline here. But so kind of going back to the combination of this is now switching to the modeling side again. So some of the motivation for kind of needing these observations was biases in global models, in climate models and weather prediction models. But then, from the modeling side of the talk, there were some idealized studies, but kind of maybe focusing more on the weather prediction side. And so I'm curious about the technical hurdle, because it's my understanding, and as kind of briefly mentioned, right, there isn't a lot of, most GCMs that are used for climate projections don't go that far. I mean, they have model levels in the stratosphere, but they don't extend terribly far, and so a lot of them struggle to even reproduce a lot of variability that occurs in the stratosphere. And so there was this discussion early in the thing about a model bias from the climate side, and I'm curious if when you look at some of the deep atmosphere models or some of these whole atmosphere models, is there a systematic improvement in that bias just by actually capturing just some of the dynamics in the stratosphere that isn't resolved in a lot of the kind of current generation of models?
Yeah, this is actually something that we want to go further into together with Jager Richter, who developed the Paris scheme, which is currently used in the vacuum to simulate or to parameterize the convective gravity waves. And so they also, together with Joan and Julio Backmeister, she has analyzed the parameterization regarding, now please apologize if I don't say that completely correctly. So they have analyzed these parameterization schemes with observations from radar measurements, and they found out that it is again the latent heating which determines whether these gravity waves, or how these gravity waves evolve and are generated, or which characteristics are generated. And what we plan to do is to continue to study if we tune specifically the constant in the tuning parameter in this parameterization, which is related to the latent heating, if we could improve the bias in the vacuum. So this is actually something that we plan to do, and next we actually plan to start this analysis this summer before we even have the data. So we want to get in a head start on that one.
Awesome. Okay, cool. That was exactly kind of my question. So perfect.
Okay.
And if I can just hop in then, in terms of the modeling centers on the U.S. side who are engaged, I was looking for that. Can you let us know who within the U.S. And which models are being utilized?
So what we utilize is, on the one hand, the WRF model, both, as I mentioned, full physics and idealized version. We also plan to include the vacuum, and then pretty much
whole atmosphere model, of course.
Yeah, the whole atmospheric community model. Sorry, and and that's the two basic models that we use. But I mean, I'm happy if you have any suggestions or if you have any opportunities for collaborations. We would be very open to also include other models as well.
Right. So one thing that does come to mind is, so with your engagement of the ECMWF, I don't know if they're prepared for this, but here in the U.S. with our NCEP operational model and our push toward a convergence for a unified coupled model for weather to climate, the influences of the stratospheric waves on on weather and climate across the shorter timescales of climate, this could be an important community to engage as well.
Okay, that's a good point. Thank you very much.
Actually, Mike, if I could interject, this is Amy Butler. I'm at NOAA, and actually just yesterday we had a meeting in the Physical Sciences Division about the new NCEP FV3 model and how to better parameterize gravity waves in that model. And there's some people working on it here, but if you want to reach out to me, I can definitely link you to the people working on this, because I think this is something we'd be really interested in collaborating with on.
Perfect. Yes, thank you very much.
Yeah, that would be really good.
Okay.
Really good to have that contact.
And one last quick question, if I can, in terms of data, providing data out for the broader community. So these data will be immediately available through for ingest at ECMWF, and if we line things up with the Weather Service here, as well.
So I have to just say that the ones that are available right away on GTS are the in situ temperature observations, because they don't need any processing or analysis at all, so they just go straight on. And then the other, most of the other instruments, we're anticipating that it's just going to take a while to get them all QC'd and the data analyzed. So we did not make any commitment to make them publicly available in the first year. So after the first year, then it'll be starting to be released. So that's really just the nature of many of these instruments are kind of experimental, and so we have to get it all working.
Right. And so ultimately, for your data, after you've done the processing, then making the data available, what are the avenues through which the broader community can access them?
So there's going to be this French Operational Center. They are going to have a website where the data are accessible, and we're going to have a mirror of that website in the U.S. And Lars Kanyas at the LASP and UCU Boulder was preliminary, taking the initiative to mirror the data at that site. So it's very much the intention to make this openly and available as soon as everything is working.
Right. And then ultimately the archival of data beyond the initial provision through websites, are there plans to have this archived by NCEI by NOAA, or is there another international body that will be archiving it?
So LMD is making a permanent archive. We're not as organized for the archive as we could be, honestly. And the one easy way to archive it is to send it to NCAR EOL, the Earth Observation Lab. That's the and that's, I would say, would be the default solution, because I'm realistic and pragmatic, and I see that everybody's concentrating on the development and analysis and processing, and people have not had time to make fancy websites. We really appreciate the effort that LMD is doing for this, because it's going to make a huge difference in the during the campaign. But I'm guessing that maybe we even wrote it down in the proposal that we'll put it in the NCAR EOL because everybody knows to go there for campaign data.
Right. Often that requires some funding, and so at least a conversation with the EOL folks. And are they involved in any of the deployment here? And they've been engaged at EOL in the program?
We tried to convince them. They came several people came to the workshop that we had initially, and because we were considering releasing drift sondes, and we did not have a strong enough science case with NSF to deploy those drift sondes. So, given what the needs were for the type of studies that we're doing, basically because you get 50 on a balloon, and you'd probably have to release them pretty quickly, and then you have nothing on that balloon for the rest of the 75 days. So, I really think that if we had found the right partner to use that drift sonde data, it could have been a really good plan to do that. And I do have to say that also the two science campaigns, certainly the second science campaign, we're supposed to be open to new instrumentation and new ideas. We're supposed to take what we learned from the first science campaign and it's still open. There are still possibilities to do new things. So if people are interested, we could try to engage them again. They were aware of everything and were invited to participate.
Right, that's good. And in terms of on the data side as well, having a conversation with the folks at EOL, the ones that maintain data archives, to help develop kind of a data management plan post-field will be really helpful for developing your plan then for our long-term archival and access. So. Okay.
Good reminder. I mean, I did write a data management plan, and I'm just wondering what I put in it because I've just been so focused on getting the thing to work. So good reminder for me and the rest of us. I'll pass that on.
Do we have any final remarks? Kevin and Victoria, do you want to say anything, any last minute things before we go on into our summit planning?
Just thank you very much. This was, I think, very informative, and we'll put together a summary of any inputs that we might be able to help facilitate in terms of both the permissions for the overhead flights or some ideas for some of these data archiving ideas and send them back to you.
Well, that would be great. We would like to feedback it. Thank you very much for allowing us to present the project, and I hope you're, as you have opportunities to spread the word and talk about it at other CLIVAR events. We'd appreciate that as well.